Hello and welcome to this surface plasmon resonance presentation.
Before we can understand surface plasmon resonance, it is vital that we understand the basic physics needed. When light travels through one medium into another, it will refract. In other words, the angle at which the light travels will change. We see this all the time in everyday life with air and water. When we place a straw in a glass of water, it will appear to bend as the angle of the light has changed. Past a certain angle, known as the critical angle, the light will in fact reflect internally, and this is called total internal reflection. When a thin piece of metal, usually gold, is placed on top of the point of internal reflection, some of the light will be absorbed rather than reflected. This absorption of light is due to plasmons. Plasmons are groups of electrons on the surface of the metal that absorb light energy from photons and begin oscillating. As energy has been transferred from the photons to the plasmons, the light intensity will decrease. We use P, or parallel plane polarized light, for this technique, as S-polarized light will not excite plasmons. A detector can then be used to measure the light reflected and, more importantly, the dark spots where light has been absorbed. When a species absorbs onto the gold, the refractive index of the medium immediately next to the metal will change, and the SPR angle will change accordingly.
So let's talk about the instrumentation. Most SPR machines operate via something called the Kretschmann configuration. The Kretschmann configuration consists of a laser which goes through a polarizing filter and then enters a prism, which is usually some form of glass with a high refractive index. This prism sits on top of a dielectric, such as a buffer solution, which is fed an analyte through a flow channel. A 10 to 70 nanometer metal film sits at the interface between the two mediums, and the metal film is usually gold or silver, as these elements are stable, conductive, and have no magnetic field of their own. This is important as upon total internal reflection, an evanescent wave is created in the dielectric, which in turn excites the electrons on the metal film and causes them to oscillate. So the lack of a magnetic field causes it not to interfere with the evanescent wave, and instead helps it excite the free electrons on its surface due to its conductivity. The reflected light is then fed into a detector which measures the intensity over some experimental value like time or progressive addition of analyte, and this change in intensity directly reflects the change in a dielectric's refractive index. This is because a change in refractive index will change the resonance criteria between the incident light and the plasmons, giving us insight into binding events, effects of changes in concentrations, so on and so forth, as these change the refractive index of the secondary medium. The detector is then connected to a sensorgram, which plots the data on a graph so it can be interpreted. There is another configuration that is similar but kind of different to the Kretschmann configuration, and it's called the Otto configuration. It's a form of SPR that relies on the same plasmon incident light coupling through total internal reflection, just like the Kretschmann. However, in the Otto configuration, the metal film and the prism have a gap between them which is filled with air. So what happens is, on this image on the right, the light will hit, it will totally internally reflect, and the plasmons, instead of being at the interface between the dielectric, or like the substrate, and the prism, it will form on the other side of the metal film, having only contact with the substrate. So, what are the advantages of the Otto over the Kretschmann? Well, it's a bit more flexible with the sensor design, as the high refractive index medium does not actually rely on the prism, it relies on the air gap to totally internally reflect. However, prism is often used as well. The air gap can also be adapted to fit different geometries and different designs where the Kretschmann may not be suitable. but ultimately whether the Otto or the Kretschmann configuration is used, it usually depends on the specific sample that is being analyzed and which fits better for that specific purpose. So neither is strictly better than the other.
The sensor on the SPR measures two main variables, the angle and the light intensity. The SPR angle can also be measured against time. A change over time can then be used to study the kinetics of an interaction. For example, ligands associating with ligand receptors bound to the surface of the gold sheet. As you can see on the graph, the angle remains constant until the addition of the ligand. As the ligand associates with the receptors, the refractive index will change and the angle will change accordingly. The angle will then steadily decrease back to the normal as dissociation occurs. SPR can also be used to determine the concentration of an analyte. A calibration curve can be created by plotting the change in response over concentration. However, this only works at low concentrations of analyte, as at high concentrations, the linearity breaks down due to activity of the ligands. The concentration of an unknown can then be determined by measuring the change in response and plotting on the curve, provided that the concentration of the analyte is low enough that it falls into the linear, concentration-dependent section of the calibration curve.
Now that we've talked about all the technical mumbo jumbo, what are the actual advantages of this technique? Well, it is very good at real-time monitoring of things like binding behavior, which makes it very useful for things like protein analysis and DNA analysis. This is because the design is simple and measures the change in light intensity over something like progression of analyte injection. This means that modifications can be made on the fly so you can gauge a better idea of what is happening while it's happening. Another big advantage, label-free detection. This is because it measures the effect of the molecule, not the molecule itself. You do not need to alter the original molecules in any way by adding fluorescent or radioactive components that bind or label the original molecules so that they can be detected. Instead, you have a guarantee that the original molecules are depicting the properties of the original molecules, not some altered compound. Another big advantage is that this technique has a high sensitivity. This is due to the electric field produced by the plasmons only having a range of around 300 nanometers. As this field is so localized, changes to the refractive index within this range have a large impact, meaning even small changes are detected. Couple this with the label-free nature of the technique, and you have a very reliable and highly sensitive technique to take advantage of. These are the main advantages. However, other advantages like low volume requirements due to the Plasmon field mentioned before, and its flexibility due to its simple design, as well as just being useful in general for new fields like nanoscience, it makes this technique very relevant. Now that we've done the good of this technique, it's only fair that we bring up the bad. The first and main disadvantage of this technique is its extremely high cost. It's difficult to get exact values on the actual machines, as manufacturers only produce prices upon request. However, even upkeep and changeable parts of the machine have high costs. For example, a histag capture sensor, which binds polyhistagged molecules, costs around 1500 USD. And this is just a sensor surface for a specific purpose. Couple this with the fact that these sensor surfaces are not reusable, as cleaning them or introducing buffer solution cannot guarantee a completely fresh sensor surface, and you end up with quite an expensive technique. Another disadvantage is that the machine needs very strict surface functionalization and experimental controls. This is because any small impurity or bad optimization of the sensor surface for your specific purpose that you're using it for, along with some shoddy temperature control or concentration control, can cause the analyte to interact with the metal film, the prism, or even other things in solution to give false positives. This is also why reasonably high concentrations are essential for SPR, as low concentrations can lead to inconsistent rates of binding and microscopic or irregular changes in refractive index. Irregular changes due to inconsistent binding will give results that do not accurately represent the behavior of your sample, and extremely small changes in refractive index can fall under the machine's noise level, thus giving false negatives. These are the main disadvantages. However, other slightly less significant but still relevant disadvantages, such as the inability to analyze large complexes, getting almost no structural information on your analyte, and only being able to do one or two analyses at a time, depending on how many channels the machine has, these also hold the method back. All in all, this is a highly specialized method that has many uses in its specific field. However, its versatility as a whole in all of chemistry falls a bit short when compared to another technique such as IR. Here are all the references used for the presentation as a whole, if you want to check any of them out, and thanks for watching.